Let me show you in practice what it means to show that two vectors are equal. So it says show that u from the previous page. I recopied that vector here for your convenience here, rs, is equal to v. The directed line segment from O to P, where O is 1, 7, and P is the point for 11. And so I've already plotted the second vector v. And now showing that the vectors are equal, all that amounts to doing is showing that they have the same component form. So the component form of u, we can see clearly is, well, how does it move you? If you start at the tail to go to the head, you move 3 right and up 4. So its component form is 3, 4. Similarly, the component form of v is also 3, 4 because it moves you 3 to the right and up 4 if you sort of travel along the vector. And so if they have the same component form, that means, everything falls into place. Remember, the definition of a vector is it has direction and magnitude. So vectors are equal if they have the same direction and magnitude. Well, if they have the same component form, then it naturally follows that u and v have the same magnitude and direction. And that means that they're equal, okay? So this is a way around. The long-winded way to do it is to find sort of the slope of each line, because that would tell you they have the same direction. Or you could find this angle in here and this angle in here. We'll talk about that later, but and then you have to find the length of both vectors, meaning the magnitude. That's a lot of work. If you just find the component form of both and compare them, if they're the same, then the two vectors are equal. So I just wanted to give you an example of how you'd show that. Let's talk about adding vectors. So adding vectors have a very nice interpretation, which we're going to examine here. So let's look at this example. U is 1, 2. So I'm going to graph this in standard position. I'm going to graph vector u. It moves me right 1 and up 2. So there's vector u. And then, oops, they're both called u. Change that to a v. That's better. That's v. V is 3, 1. So here's how I want you to view adding vectors. We're going to add u plus v. And we're going to see that the algebra, or the arithmetic, I should say, is exactly the way we'd want it to be defined. So you take a ride on vector u, and it moves you right 1 and up 2. At that point, from here, you're going to take a ride on vector v, which moves you 3 to the right and up 1. So there's vector v. So I took a ride on vector u, then on vector v. And the result is a vector that took me from the origin here to this point right here. So the result is this vector here, which I'll put in red. So that red vector is u plus v. It's the result of traveling on u and then traveling on v. And so this is called I'll call this the head to tail, or tail to head rather. method, which is a geometric method of adding vectors. To add two vectors, you take the first one and the second one, and you line up the second one such that its tail is the old one's head. And where you end up, the head of the second vector, if you draw a line from the beginning of the first vector, the tail of the first vector to the head of the second, that is the vector that results from adding them. So notice what the vector in red does. It moves you 1, 2, 3, 4 right, and 1, 2, 3 up. So it's 4, 3. And notice if we just do the addition here, component-wise, 1 plus 3 is 4, and 2 plus 3 is 1. So vector addition is very easy and intuitive because the way you add vectors is exactly the way you would want to if you had to choose. Right? Add the x components and add the y components. And graphically, the tail to head method gives you a sense of how the vectors are moving you when you combine them. And so that's all I'm describing here. If this is vector u, and this is vector v, then this is vector u plus v. Okay. So let me do an addition down here. Let's do a practice one. I'll let you practice it. I want you to sketch the picture. I want you to sketch 3, 3 plus 3, 1 plus 3, negative 2 plus 7, 0 and I want you to see what you get. So I want you to do this. I want you to pause the video, actually draw the tail to head method of this addition that represents this addition, then add the components and see if you get the same thing. So I'll let you pause it and then I'll do it out for you. All right, welcome back. So 3, 3, we'll start here. 3, 3 moves you 3 to the right and 3 up. And then from here, we take a right on 3, 1, which moves you 3 to the right and up 1. From here, we go 3 to the right and down 2. Then we go 7 to the right, 7 to the right, and 0 up or down. So 1, 2, 3, 4, 5, 6, 7. And we're done, right? And so the question is, the result of that summing amounted to taking this vector here, taking the vector that started here, and ending here. In other words, taking a ride on all those vectors got you to this point over here, but we also could have just gone right there by taking a ride on the red vector here. And what are the coordinates of the head here? That'll tell us the component form of this red vector. Let's see, it moves you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 to the right and up 2. And let's just check. Just check to make sure. 3 plus 3 is 6, plus 3 is 9, plus 7 is 16, so that checks out. And three plus 1 is 4, minus 2 is 2, plus 0 is 2. So that checks out. So vector addition, if you want to be formal, the vector AB plus the vector CD is simply A plus C, B plus D.